Your visual cortex is an evolutionary masterpiece. In a single second, you process roughly 10 billion bits of visual data. You spot a face in a crowd, read a handwritten note, or catch a ball, all without a single conscious thought. But for a computer, vision is a nightmare. For decades, the simple act of distinguishing a cat from a dog was the hardest problem in artificial intelligence. To understand why, we have to look at what a computer actually sees.
To a computer, an image is just a massive grid of numbers. Let's take a standard input size, 224 by 224 pixels. If this is a color image, we have 3 channels, red, green, and blue. That gives us 224 times 224 times 3. That is 150,528 individual numbers. Each number is just an integer between 0 and 255. There is no concept of ear or whisker here. A photo of a cat and a photo of a dog are just 2 slightly different arrays of 150,000 numbers. There is no inherent structure.
Your first instinct might be to use a standard neural network, what we call a fully connected network. We could flatten that 3D image into a long 1D line of 150,528 numbers and feed it in. But this fails catastrophically. Here is the math. Suppose your first hidden layer has just 1,000 neurons, a modest number. Because it's fully connected, every single one of those 150,000 input pixels must connect to every single one of those 1,000 neurons. That creates 150 million weights, and that is just for the first layer. A model this size is nearly impossible to train. It would memorize the training data instantly and fail on anything new. We call this the parameter explosion.
The fully connected approach has a deeper flaw. It ignores space. In a standard network, the pixel at coordinate 0, 0 and the pixel at 223, 223 are just 2 inputs. The network doesn't know they're far apart. It doesn't know that pixel 0, 0 is right next to pixel 0, 1. But in images, locality matters. Pixels form edges. Edges form shapes. By flattening the image, we destroy that spatial structure. We need an operation that respects the grid.
Imagine a small magnifying glass. Let's say it's a 3x3 grid. We call this the kernel or filter. We place this kernel over the top left corner of our image. We look at the 9 pixels underneath it. We multiply the kernel's values by the image's pixel values, element by element, and sum them up. This gives us one single number. Then we slide the kernel over one step and do it again. We scan the entire image, left to right, top to bottom. We aren't flattening the image anymore. We are scanning it, preserving the spatial relationships.
The magic lies in the numbers inside the kernel. Let's look at a specific example. A 3x3 kernel where the left column is -1, the middle is 0, and the right is +1. If we place this over a flat color, the left and right cancel out. The sum is 0. But what if we place it over a vertical edge? If the left pixels are bright and the right pixels are dark, the math produces a huge number. This simple matrix is a vertical edge detector. We don't have to program these. In a convolutional neural network, or CNN, these kernel values are learned. Through backpropagation, the network discovers the optimal kernels to detect edges, curves, and textures. We control this scan with 2 numbers, stride and padding. Stride is the step size. A stride of 1 means we slide 1 pixel at a time, keeping high detail. A stride of 2 means we jump 2 pixels, which effectively cuts our output width and height in half. Then there's padding. Notice that a 3x3 kernel can't center on the very edge of the image. It would hang off the side. This shrinks the image slightly with every layer. To fix this, we use same padding. We add a border of zeros around the image so the kernel fits perfectly at the edges, keeping the output size identical to the input.
Here is where CNNs truly solve the efficiency problem. In that fully connected nightmare, every connection had a unique weight. But in a CNN, we use the same kernel across the entire image. If a vertical edge is important in the top left, it's also important in the bottom right. We call this weight sharing. A 3x3 kernel has just 9 learnable parameters. Even if we have 64 different kernels, that's only 1,728 parameters total. Compare that to the 9.6 million parameters required for a comparable fully connected layer. That's a reduction of over 5,000 times. We aren't just saving memory, we are encoding a fundamental truth about vision. A feature is a feature, no matter where it is.
When we stack these layers, magic happens. The first layer looks at raw pixels and finds edges, vertical, horizontal, diagonal. The second layer looks at the map of edges and finds patterns, corners, circles, textures. It combines the simple into the complex. By the time we reach layers 4 or 5, the network isn't seeing pixels anymore. It's detecting eyes, wheels, or fur. The deeper we go, the more abstract the understanding becomes. This is hierarchical feature learning, and it mirrors how the mammalian visual cortex works.
Sometimes too much detail is a problem. We want to know if there's a cat ear, not necessarily that it's at pixel coordinate 4592 specifically. We need translation invariance, the ability to recognize the object even if it shifts slightly. We achieve this with pooling. The most common type is max pooling. We slide a window, say 2x2, over our feature map and just take the maximum value. We throw away the rest. This shrinks the data size, reduces computation, and makes the network robust to small movements. It forces the model to focus on the existence of features rather than their exact location. This is the architecture of modern vision. We start with a meaningless grid of 150,000 pixels. We use convolution to detect local features efficiently. We use weight sharing to find those features anywhere in the image. We stack layers to build a hierarchy from edges to objects. And we use pooling to focus on what matters, not just where it is. We haven't just built a calculator. We've built a system that learns to see.